The discovery of the electron happened in 1897. That was when the paper was published about the cathode rays and about the electrons, which we called the cathode rays in the beginning. The proton was discovered in 1919, or formalized, after these experiments with Rutherford and with the alpha particles. And the neutron took a while longer because the neutron's harder to detect because it doesn't have any charge. It has a mass. Protons and neutrons have about the same mass, very close. But the neutron has no charge. And we figured out in 1932 that neutrons existed. So literally less than 100 years ago, we didn't even know that neutrons existed at all. All right, and now here is where I go down and tell you about the modern, I guess I should say, the 4th grade version of what an atom is. I'm going to draw a picture of that. We're going to talk about this a lot in the next lesson also, so I'm going to repeat myself. But I want to break down your barriers. I have to break your barriers down because I know you're watching this and you're thinking, I know what an atom is. I've seen pictures of that. Well, you don't. Trust me. Nobody knows what an atom is. Anybody that tells you they think they know what an atom is wrong. They don't. Nobody does because it's a quantum object and none of us can really interact with quantum objects on we touch everything. Everything's quantum, right? But I mean, an individualized single atom is a quantum object, behaves differently than the large things around you. So none of us have direct experience with what they really look like. So after these things, and we realize the center of the atom contains the positive charge, the mass of the atom, we wrote down the following model. The following model, which was used for many, many years, and it's still what is taught in 4th and 5th grade, around the world, or younger even. Basically, in the center of the atom, you have these things called protons, and you have these things called neutrons. So let's say you have 2 of these protons, which are positive charges, and you have 2 other particles called neutrons, which are no charge at all, and they're all bound together. And we said that they're stuck together because there's a strong nuclear force that's the strongest force that we have that's holding them together, even stronger than the repulsion happening here between the 2 charges. That's what's holding the nucleus together. As you build bigger and bigger atoms and make them heavier, the nucleus gets physically large where the strong nuclear force can no longer hold it anymore, and so then the electric repulsion takes over and the thing just starts to disintegrate. We call that radiation. And of course, when those radioactive bits hit you and they hit your cells, they destroy your tissue on a microscopic level. They destroy your DNA, and that's why you get radiation sickness. That's why radiation's bad. It's like trillions and trillions of little microscopic bullets hitting you and destroying your little chemical nucleotides inside of your DNA. So this is the nucleus. And surrounding this nucleus is what we call electrons. So I'm going to draw 2 of them here, and they have negative charge. So the protons have exactly the same charge as the electron, except they're opposite, right? One of them's positive, one of them's negative. And the story goes that these electrons are orbiting the nucleus, right? And it's a good model to have. I'm not saying throw this model in the trash can. I think of this model myself in certain situations. But what you're going to find is that as you learn more and more about chemistry and as you learn more and more about physics, this model of the atom, it just isn't true. Because electrons are not really little balls like this. Protons also are not really little balls like this, but that's another story for another day. But these electrons do have what we call angular momentum when we talk about quantum mechanics, and that's why in the early days they thought they physically rotated like little balls, like little solar systems. Right, they go around like this. But this is a good model to have in your mind in the beginning because you can understand that these electrons are in a certain orbit, which is a certain distance away from the nucleus. And what we now know is that if we pump energy into this thing, like if we heat it up, then these electrons will go out to a higher orbit, right? And when they decay back down, they're going to release a photon, which is light. So whenever it's a useful model to have because when you put a piece of metal in a campfire and pull it out and it's glowing, the reason it's glowing is because the fire put energy into the metal, into the atoms. That energy goes into the electrons, which they kick them up into higher orbits. The energy has to go somewhere. It go into these very light electrons, which gets kicked up into higher orbits. Okay? And then when eventually one of these electrons falls back down, when it falls back down, it releases a photon of light. And that photon of light is what you see. So everything that glows, glow-in-the-dark sticker, glow-in-the-dark, anything really that emits light of any kind, it's LED, lasers, it's because of electrons moving around, because that's what's basically doing it. Now that's more of a physics thing, but we also use that kind of thing in chemistry as well when you get to the more advanced material. All right. But as I said, this is not really the right model of the atom. What is the right model? Nobody really knows, but I will tell you something a little bit closer to the truth. These electrons, right, that we're going to learn about later, and also the protons and the neutrons too. We'll save that for later. These electrons, they're really wave-like things, right? They're wave-like entities, and we know this because we've done lots of experiments with electrons. They behave more like waves than they do anything else. We don't notice it because we're so gigantic compared to these tiny little waves, so we don't notice the wavy nature of electrons or protons or anything else, but it's true. They all have a wave-like character. Light waves also have a particle-like character, and electrons are matter, but they also have a wave-like character. So everything has a wave-like character and a particle-like character. Everything does. Everything you've ever encountered in your whole life is basically a wave at its core that can also look like what we call a particle to us, okay? So if I had to draw something a little bit closer to what the actual structure of the atom is, and this is not going to be right either, okay? So please just keep that in mind. Then what I would say is, and not just what I would say, well, what we know is that the nucleus, yes, has these positive protons and so on, but the electrons are not really little balls that are just orbiting around here. The electrons are really a wave. And the reason that they're this far away is because this wave has to close in on itself. So it's like a wave that goes around and it has to close in on itself to be a wave. So I drew like this lopsided potato thing, but you have to, in your mind, imagine it vibrating. It's like goo, 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 goo. It's like vibrating like a string, right? Like a string that you tie to the wall. If you tie a string to the wall and you start vibrating it, you can set it up where it's like goo, 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 goo. It's like doing that little wavy thing. That's called a standing wave, because you have one wave going toward the wall, one wave bouncing back from the wall, and they kind of interact, and they do that. If you set it up right, you can get that standing wave oscillation thing happening, and as long as you keep doing it, it keeps making that effect happen. Electrons are more like a wave, and the reason that they have to be a certain distance away from the nucleus is because they have to form a closed wave pattern, otherwise they're not an electron anymore. And so again, you have to imagine it vibrating like kind of like this. And when I put energy into this thing to kick it out into a higher orbit, then what I'm doing is I'm making more wiggles in the electron out here. So maybe it's doing something like this a little farther away, but it still has to close in on itself. That's what a higher energy electron looks like. And then of course, when it decays back down, because it is attracted to the nucleus, right? So it does want to decay back down, it goes back into this state. But it can't get into a lower state than this because it has to form that standing wave thing in order to be called an electron. Okay, now, I told you all education was a series of lies. I don't expect you to remember this or know this or even care about this right now, because we're just starting our path on chemistry. But like I said, I want to break down your barriers so that you know that stuff is coming that's going to blow your mind. I want to blow your mind a little sooner. So stick with me and I'll talk to you about something further. This even really isn't a great model of the atom, okay? Even though it's pretty good, it's much, much closer to the quantum mechanical nature of the electron and the atom, okay? It's much, much closer because it really does convey the wave nature of what's going on. But the question that you get over and over and over again is, if electrons are negative and protons are positive, which are in the nucleus, and they're attracting, why doesn't the electron just slam into the nucleus and just live there? Like, why do we have this orbiting business at all? Well, when I phrase the question, you see how I put my fist here and I said, the electron is negative and it's right here, and the protons are positive and and I put my fist up like this, right? Because you see, subconsciously, I want to believe that these electrons are little balls, but they're not little balls. These electrons are extended things called waves. This whole thing is the electron, not just this little part of it. The whole thing is what we call an electron. Let me ask you a question. If you're at the beach and you watch the waves come into the beach, and I ask you, where is the wave? Then you're going to point to the crest of the wave and you're going to say it's right there. That's it. But actually, if the crest is right here, what if you go down from the crest a little bit? Is this part also the wave? Or is it only the top part? Or how about on the other side of the crest, when it comes down over here, is this part also the wave? Well, yeah, it's all part of the wave. So where's the wave? The wave is not something that is right here. It's an extended thing. because a wave by nature is an extended thing. In fact, the whole ocean is covered in water. And you could make an argument that the wave really is the entire surface of the ocean. It's just there's a localized crest right here, but the wave really goes down and extends throughout the entire surface of the ocean. So really, if the wave, work with me here, if the wave represented where a particle would be if you measure it, then where the wave is big, you would expect the particle to be mostly there. But where the wave is small, then you would not expect to see the particle at the small parts of the wave. If you adopt that model, then what you come up with is that the whole surface is really the electron, is the wave. But where the wave is a maximum there is just the most probable location for what we call the electron. Because when we measure the electron, we say it's there. When we measure the electron again, it's going to be in a different location, right there. Now, in the old theory, we say that's because the electron's just going around and around and around. And you might measure it, and it might be in different locations, but it's much more complex than that. Actually, the electron is a wave that extends all throughout space. It has a most probable location in this orbit around the atom, but it can be in different locations, and if you measure it enough times, you will measure that it is not always in this nice little dotted line, which we call an orbit. And it's not going to always be in this nice little location here. Sometimes it's going to be a little farther away. Sometimes it's going to be a little closer to the nucleus. But its most probable location would be at this distance, the red line here, a distance away from the nucleus. So I come back to my original question. Why doesn't the electron just crash into the atom? Or the nucleus, because the nucleus is positive, the electron's negative. Why doesn't it just smash in and live there? They're attracted to each other. These are deep questions that I don't want to say they don't have answers. We know why, but they're not easy answers. There's a lot of reasons why that doesn't happen. One of them is because of when we learn quantum mechanics later, you're going to learn something called the Heisenberg uncertainty principle. Basically, it says that you cannot know the position and the velocity, also there's energy wrapped in there, a different way to formulate it, of a particle at any given time, right? And if the electron crashes in onto the nucleus, then you're going to know with very high certainty where that electron is. It's on the nucleus. And so that means it has to be moving very, very, very fast, which means it's going to escape the nucleus. Because you cannot have a zero position and a zero velocity of anything all the time. It violates uncertainty in quantum mechanics. I told you this will bake your noodle because this is not common sense. You don't see this happening, but this is true of electrons. So it cannot live on the nucleus because if it does, we would know exactly where it was. And if we know exactly where it was, then it violates uncertainty because then it would have to have a very high velocity, in which case it would, or momentum, it would have to escape the nucleus again, right? And the last thing I will tell you is to blow your mind a little bit further, that this thing here, I've drawn it as a two-dimensional little wavy thing. Remember, atoms are three-dimensional things. So when I'm talking about the wave nature of the electron, it's not just a dotted line that's around that's vibrating. It's a three-dimensional thing, three-dimensional spherical thing. In fact, the innermost electrons to atoms all have a spherical, what we call a spherical distribution, a spherical wave function, right? So the wave nature of it is spherical in its shape. And actually, it turns out that these waves, you might say, what do they represent? Okay, you tell me the electron's a wave. What's waving and what does it represent? Well, what we say in quantum mechanics is that an electron is represented by a wave function, which is a wavy thing, and we can do calculations with that wave function, and the wave function represents the probability of where the electron will be if you measure its location. In other words, if you set up a detector and you measure the location, you're going to see where the electron is. If you set up a detector and try to measure it, maybe it's here. And then you do another experiment and you find out the electron's here. Maybe it's here, maybe it's here. Every time you do the experiment, you find a new location for the electron. But the wave nature of the electron is extended in space, and every time you measure it, you get a different location, but the shape of the wave function surrounding the atom tells you where you're likely to find the electron. It tells you where you're likely to find the electron. So one thing we're going to learn about later is if this is the distance away from the nucleus of an atom, and this is the probability, I'll put P, the probability of finding the electron there, and right here is the nucleus, then what happens is you have a curve that looks something like this. This is the probability of finding an electron surrounding the hydrogen atom. And notice there is a peak right here. We call this peak A, which is, or A naught, which is the Bohr radius, because this is the Bohr model of the atom. We'll talk about, you know, it's when I say Bohr, it's B-O-H-R, not like bored, it's B-O-H-R. And so what we find out is because of the probabilistic nature of quantum mechanics, and because these things are waves, and because like on the surface of the ocean, the wave is extended everywhere, right? Then there really is a probability that the electron will be really, really far away. Think about the surface of the ocean. The wave crest is near the shore, but the ocean extends way thousands of miles away. And if the crest of the wave is an indirect measurement of the probability of finding an electron when you measure it, then you're much more likely to measure it right here, which is what we draw. This is this dotted line called the Bohr radius. We say the electron's here. But actually, if you measure it again, it might be a little closer to the nucleus, because the nucleus is right here at the origin. It might be really close to the nucleus, but it's going to be a lower probability of finding it here. It might be really far away from the nucleus, but it's going to be a low probability of finding it there. I might measure the electron position around an atom, and because this thing never gets to zero, I have a small probability of finding that electron over near the nearest star system, Proxima Centauri, 4 light years away. It has a very small probability of being anywhere in the universe. Way over there, millions of light years away, because this mathematical function never gets to zero. So there's always a small chance of it being over there. And there's a small chance that the electron will be found nearer and nearer and nearer. And actually, this curve does not hit exactly zero. There is a very small probability that you will find the electron on top of the nucleus. So when I asked you the question, I said, hey, a lot of people ask me, why doesn't it just crash into the nucleus? And I told you, I said, well, actually, if it did that, then it would violate uncertainty, and so you never find it there. I lied to you again. Actually, there is a small probability of the electron being in the location of the nucleus. It's very small. But if it happens, then what happens is something called electron capture. You don't need to know this for chemistry, but it's just something to satisfy, hopefully, your curiosity. Is basically a proton can absorb the innermost electron of an atom and turn into a neutron by absorbing an electron. And in that process, it releases another particle called a neutrino. This is way beyond the scope of chemistry, okay? I'm just mostly telling you this for completeness. People want to know, why don't they crash in? Okay, I'm telling you, it's possible for that electron to have a position on top of the nucleus. It's incredibly small to happen, but it can happen. And when it does happen, the proton in the nucleus absorbs it, turns into a neutron, and releases a neutrino, which is another type of radiation. It's another particle that can come on out. There's a whole universe of these little particles that are way beyond the scope of this, but that's called electron capture. So I told you, education was a series of lies. First, we say, hey, let's go ahead and do some experiments. And let's see what this radioactive stuff means. There's 3 kinds of particles that come out. One's got positive charge, one's got negative charge, and one's got no charge at all. And we can learn something from trying to deflect them with these plates, and we can figure out the charges. And then we say, all right, the positive and negative charges, maybe they comprise what atoms really are. So let's say that they're just evenly distributed there. That's our first model. Let's test it and see if it's true. How are we going to do it? We're going to shoot a bunch of alpha particles, which are positive charges, high mass, at a very thin target. But surprisingly, they bounce off. So it can't be this model, because if it was this model, we would never get anything bouncing back at us, not with this magnitude here. So we say instead of that, maybe the nucleus is concentrated with the positive charge, and maybe the atom is mostly empty space, so whenever the incoming particle hits the nucleus or gets close to it, it bounces and ricochets back. That's probably closer to the truth. So then we discover, or we write down this thing called the Bohr model of the atom, where the nucleus has the protons and the neutrons. The protons are all positive and the neutrons are neutral. Surrounding that, we have these electrons and negative charges, and that makes perfect sense because we have the planets in the solar system and they go around the sun. So by analogy, maybe the electrons just go around and around like little solar systems. Everybody's happy. And then they finally say, well, wait a minute. Actually, if we shoot a beam of electrons at a double slit and we do a double slit experiment, they actually behave like waves more than they do behave like particles, because when we shoot light and we do these experiments with light, we see an interference pattern between the crest and the trough of the light waves. But when we do the same exact experiment with electrons, which we think are particles, we actually see a light and dark pattern of interference. So we suspect that electrons are also waves. So then they developed this whole theory called quantum mechanics and say, well, wait a minute, if these things are waves, then they're not just at one location. Just like a water wave near the shore is not at one location, it's just got a range of locations. Whereas the wave is everywhere, it's just a maximum right there. Maybe electrons are like that. So then maybe they're not just these little balls orbiting, maybe they're vibrating waves that are surrounding the atom. And if that's the case and you go through the quantum mechanics, you can, with a lot of math, come up with a plot that looks like this that shows you the probability of finding an electron surrounding an atom. And what you'll see is there is a maximum probability, which is where we say the electron orbits. It most likely is going to be found in the orbital location. That's why we thought that they orbited in that orbit when we did the original calculations. That was its most probable location. But the electron can be found farther away. In fact, the electron can be found across the universe with a very small probability. And the electron can be found closer to the nucleus also with a very small probability. In fact, the electron can be found inside the nucleus with a vanishingly, incredibly small probability. But if that happens, the proton's going to suck it up, turn into a neutron, and radiate out something called a neutrino. It's a radioactive process. So, education is a series of lies. And I'm sure that as you learn the things that I'm trying to teach you, and you go on and discover the next best thing and the next theory and the next experimental result, right? That you are going to prove some of the things that I have said wrong. I hope you do, because it's the only way that we go farther in this world. I could have stopped this lesson in the beginning and just talked about the discovery of the particles, and that's cool. But what I really wanted to do is share with you the path and the journey of where we are today. There is a whole lot of math that goes into this. This stuff I'm drawing on the board, it's not a result of just somebody saying, oh, maybe it's like this. It's a mathematical model with equations that we can predict things from. And quantum mechanics is our most accurate theory. It is very, very accurate to many, many decimal places. And without quantum mechanics, we could not build computers, we couldn't build phones, we couldn't build anything with modern technology. So we're reasonably sure it's correct. Doesn't mean it's complete. It may not be complete, but we're reasonably sure that it's very close to being what actually matter is made of. So I'd like you to watch this a few times and then follow me on to the next lesson. We're going to get back more into the realm of chemistry and how the chemical reactions happen as we move forward with talking about the atom. Learn anything at mathandscience.com.